Welcome to topic number 16 in Richard James Mathematics Resources, and this one is entitled Set Theory. One thing that all candidates can attest to is that the questions on the examination paper are more challenging than understanding the concepts that are taught in set theory. There is no doubt that the concepts are very simple. Merely understanding concepts is not the reason why the topic is introduced in the CSEC syllabus. Most times, examiners test candidates' ability to reason and to pay attention to very important details. For example, on one examination paper, the universal set contained multiples of 3. The candidates were then required to list the set of even numbers, and that was required to be a subset of the universal set. Some candidates proceeded to list 2, 4, 6, 8, etc., neglecting the fact that the universal set only contained multiples of 3. While at the university, a course in the Department of Language and Linguistics required that we use set theory to analyze an argument in order to determine its validity. For most students, this was the most difficult part of the course. This is because it required more thinking than the others. A course should not only prepare us for an exam. The things that we learn should help us throughout our entire life. During the campaign season of one general election, I was able to point out all of the flaws in the argument of a particular political party to my friends. They thought I was silly until 1 to 2 years after the party won the election, and they start to feel the repercussions. My education enabled me to see the economical conditions before it happened. A set is a collection of items with at least one thing in common. A set is defined by using a capital letter, its items are separated with commas, and they are enclosed in braces. These brackets are called braces, and they are used to enclose sets. There we have the capital letters. These are the capital letters that are used in naming the sets. Items in a set are separated by commas, and if we look in set A, we have 2 commas separating those 3 items. In the other set, we have 1, 2, 3, 4 commas separating the items. If an item B belongs to a set B, we say that the item B is an element of the set B, and we write it like this: B, this symbol, an element of, that's what it means. So B is an element of B. If the item B does not belong to the set A, we say that the item B is not an element of the set A, and we write B, this means not an element of A. So B is not an element of A. So there we have our set A, and what about the element 2? We notice that the element 2 is in that set. Therefore, we conclude that 2 is an element of the set A. By looking at all of the items in the set A, we will realize that 10 is not in the set A. So in that set we have 2, 4, 6, and 8. 10 is not in that set. Therefore, 10 is not an element of that set A. There we have something that looks like a flatted E. That is the common Greek letter epsilon, and it means, in set theory, an element of. The null or empty set is a set that contains no element. It is symbolized by this symbol, the common Greek letter phi, Or we will symbolize the empty set by having the brackets with no element in between. So this symbol is the common Greek letter phi, and it is used to represent the null or empty set. The set contains no element, and of course this symbol is the common Greek letter phi. The cardinality of a set A is given by NA, and it is the number of elements in A. There we have two sets. V is equal to the set of letters A, E, I, O, U, and P is the set of numbers 2, 3, 5, 7. So count the number of elements of V. 1, 2, 3, 4, 5. Therefore, the cardinality of V is 5. NV is equal to 5. Also, we will count the number of elements of P. There are 4 of them. The cardinality of P is 4. NP is equal to 4. If for every B an element of B, B is an element of A, we say that B is contained in A, or B is a subset of A. So let's do that again. If for every B, that means every element that is an element of the set B, if that element is also in A, then we say that B is contained in A, or B is a subset of A. And we will write B with these symbols mean a subset of A. If for every D that we have in the set D, D is not an element of A, we say that D is not contained in A, or D is not a subset of A. And this is how we write it. The same symbol that we used before, but we have a slash through it. This means D is not a subset of A. There we have set A, 4, 5, 6, 7, 8, and 9. Those are the elements of A. And we have other sets, B, C, and D. So now we are going to compare the elements of the set B. What we are testing here, we are testing to see if B, C, and D are subsets of A. So we compare the elements of the set B with the elements of the set A. That is what we are going to be doing now. We find 4 present, 5 is also present, and 6 is present. However, 3 is not present in A. Because 3 is not present in A, we conclude that B is not a subset of A. So the element 3 in B is not in A. B is not a subset of A. We are going to do a comparison also of the elements of set C with the elements of set A. We have 6 present, 7 present, 8 is present in A also, 9 that is in C is also present in A. So we see that all of the elements of C are present in A. All of the elements of C are also in A. C is a subset of A. Let us do a comparison with D also. As a matter of fact, we realize that the first one, 10, is not present. So also 11 is not present, 12 is not present, 13 is not present. There is no element in D that is in A. D is not a subset of A. Right. Although most of the elements of B are in A, this does not make B a subset. All of the elements of B must be elements of A, as in the case of the set C. D is far from being a subset of A. It has no element that is in A. The number of subsets of a set A is given by 2 to the power of NA, and we know what NA is already. NA is the cardinality of A, which represents the number of elements that are in A. Determine the number of subsets of the following set and write them down. So we have A is equal to the set that contains A, B, and C. The number of subsets of A will be 2 to the power of NA, 2 to the power of the cardinality of A. NA is 3. So the number of subsets will be 2 to the power of 3. And 2 to the power of 3 is equal to 8. The set A has what? 2 times 2 times 2. 3 2's multiplied together. And that gives 8. So we will have 8 subsets. As a matter of fact, Richard James Mathematics Resources made use of indices in the first volume. So that topic can be consulted in order that we may verify that this is correct. Write down the subsets of A beginning with the set that contains no element. So we are going to write down all of the subsets of A. And the first one is the null or empty set. So we are going to move on to the sets that contain one element each. A, the set that contains B, the set that contains C. Then we are going to list the sets that contain 2 elements. So we are going to go on to the subsets that have 2 elements each. So A will go with B, and in the next subset, A will go with C. Then what next? Of course, B will go with C. So those are all the subsets that have 2 elements each. Finally, the subset will contain all 3 elements of the set A. So the final subset is equal to the set A, and we have all 3 elements right there. So we are going to determine first of all the number of subsets of the set B. That is equal to 2 to the power of NB, 2 to the power of the cardinality of B, or 2 to the power of the number of elements in B. And of course, we have 1, 2, 3, 4 elements in B. So 2 to the power of 4, and that is equal to 16. And as our topic in indices would have indicated to us, the set B has, what does 2 to the power of 4 means? We have 2 times 2 times 2 times 2, which is, of course, 4 2's multiplied together, and that will give 16. So write down the subsets of B beginning with the set that contains no element. So the subset without any element will go first. That is our null or empty set. And then of course we are going to move merrily on to the sets that contain one element each. There we have the first one. There's a second. And of course the set that contains 3 and the set that contains the element 4. So we have exhausted all of the subsets that have one element. So we are going to list the subsets that contain 2 elements this time, and of course we are taking a systematic approach by using 1 and combining 1 with 2. So we have the set that contains 1 and 2, and of course keeping our attention on 1, we are going to compare that with 3. We have 1, 3. Then the 1 will be coupled with the element 4, and then we have 1, 4. Continuing, we are going to move on to 2, and we'll couple 2 with the others. 2 with 3, the subset will contain 2, 3. Then the other subset will be 2, 4. Right. Now that we have exhausted 2, we'll move to 3. 3 coupled with 4, and we have that subset with 3 and 4. Then we will not have any more subset that has 2 elements. Now we're going to move on to the subsets that have 3 elements. Our systematic approach will, in this case, be explained by this statement that we have right here. By leaving out one element each time, list the subsets that have 3 elements. And of course, we are going to leave out the last element first. So, leaving out 4, our first subset will be 1, 2, 3. Then, we leave 3 out, and our next subset will be 1, 2, 4. Leave out 2 next. Our next subset will be 1, 3, 4. And our final subset that has 3 elements will be the one that does not have 1 as an element. So that one will be 2, 3, 4. Then we'll move merrily on to the final subset, and that will contain all of the elements of the set B. So there we have them. We expected 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. The null set is a subset of every set. Every set is a subset of itself. Notice that a particular order was maintained when attempting to list the subsets. This was done in order that no subset would be left out and no subset would be repeated. Students are encouraged to use similar systems of order when attempting to list subsets. We are going to continue with our definitions. The intersection of two sets A and B, called A intersection B, and written like this, with this thing that looks like an N, is the set that contains the elements that are common to A and B. So we have two sets A and B, and we are going to find their intersection. So in order to do that, we are going to identify all of the elements that are present in both sets. And that set will be A intersection B. So we have 6. We find 6 in both. So 6 will go there in our intersection. And 7 is in both. So that is a part of our intersection. Also, we have 8 in both sets. 8 is included, and 9 is not to be left out. It is present in both sets. So that is our set A intersection B. It has all of the elements that are present in both A and B. When two sets have no element in common, we say that they are disjoint. Notice that the intersection of two sets is defined as another set. When listing elements of the intersection of two sets, it is appropriate to enclose them in braces as we would any other set. The union of two sets A and B, called A union B and written A with a symbol that looks like a U, is a set that contains all the elements of A and B. When writing down the union of the two sets, common elements are not repeated. So, the elements that are common, they are not written twice. So let us identify all of the elements that are present in both sets. And, of course, that will be A union B. So 4 is present, 5 is present. Now notice that although 4 and 5 are not present in both sets, they are included. This is because we are taking note of every single element that is present in both sets. And of course we have 6 is a common element and it is not repeated, so we don't have 2 6s down. 7 also, 1 7 is written down. 8 in A and B, but it is written down once. And the 9, the final of the repeated elements, is also written once. No more common elements. We have 10 present in B alone, and 11 is also present in B alone. So this set, A union B, contains all of the elements of A and B. As a matter of fact, if we look in this set, we'll realize that we find all the elements of this set present and all of the elements of this set also present. The union of two sets is also defined as another set. When listing the elements of the union of sets, it is appropriate to enclose them in braces. Notice also that the elements that are common to both A and B are listed only once. The complement of a set A is called A complement and is written A with, should have been a shorter slash, but we are in the computer world. We have to make use of the one that we have. So it is A. If you do Spanish, it should be somewhat of an accent or something that looks like an accent. Or it is something that looks like a slash that is raised. Like A to the power of, but the power is a slash. And, of course, that means the complement of A. It is a set that contains all the elements that are not in A. And of course, if we should define all the elements that are not in a particular set, we will have to count everything in the world, and the complement of a set is indefinitely and ridiculously large. However, the complement of a set is usually defined relative to some predefined universal set. A universal set is a set that contains all the sets that are being discussed in a particular situation, and it is given as U for the universal set, or this special capital Greek letter, and we'll see and hear its pronunciation in a short while. So that symbol is the common Greek letter Xi, pronounced Xi as we would pronounce KSI. A Venn diagram shows sets and their relationships to each other. So we are going to use Venn diagrams now, and a Venn diagram is one that shows the sets and their relationships to each other. And we are going straight to Venn diagrams because we have to make use of the complement. We are going to start our look at Venn diagrams. Given the following sets, and there we have them, Represent the sets in a Venn diagram. The universal set is represented by a rectangle that is large enough to contain two circles that will represent the sets A and B. So of course, this is our universal set, and this is our common Greek letter Xi. It represents the universal set. Then we will have the set A and B. They are going to be inside of that Venn diagram. So the sets A and B have common elements. How do we know? There we have 2 that is present in A and B, and also 4. 6 is present in both sets, and finally we have 12 present in both sets. So we know that the sets will have an intersection. A and B will therefore be represented by circles that overlap each other. When completing a Venn diagram in which a universal set contains 2 other sets, the elements common to the 2 sets are inserted first. So what are the common elements? 2 goes in first, and another 4 next, and if there's any other, it will go inside the intersection. Of course, when completing a Venn diagram that contains 2 sets, the elements that are in the intersection of the 2 sets will go first. Then of course, we will include the unique elements of A. What elements are in A that we do not have in the intersection? 1 and 3. Do we have any other? No, sir. This is followed by those unique to B. Those elements that are in B that are not in the intersection, they go next. Right. And finally, if there is any element that is unique to the universal set, that is, they belong to the universal set but do not belong to A nor B, they are the last to be included. The last but not the least. They are placed in the rectangle, the universal set, but outside of A and B. 5 is one of them. 7 is another. Not in any other set, but in the universal set. And finally 11. So those are the elements that are not in A and are not in B, but they are inside of the universal set. We may then proceed to use the Venn diagram in assisting us to answer the questions by finding the required set. So find the set A complement. Of course, the set A complement contains all of the elements that are outside of the set A. That is, all of the elements that are not visible. So the elements that are not visible are the elements outside of A. See, we have covered the set A, so we have the elements in A complement. We have 5, 7, 9, 11, and we have 8 and 10. However, it is going to be more appropriate to write the elements in numerical order. So the complement of a set is also a set, and its elements are appropriately enclosed by braces and separated by commas. The elements should be in numerical order where applicable. So, a similar approach may be taken in finding the set B complement. All of the elements that are not in B, so B complement is a set of elements that are not in B. All of the elements of B are concealed. We are therefore talking about all of the elements that are revealed. So we have 1, 3, 5, 7, 9, 11, and those elements are in B complement. Find the set A union B. A union B is a set that contains all of the elements of A and B and is represented by the entire shaded region. This is our entire shaded region, and that represents A union B. And we are going to write all those elements down. So write down all of the elements in the entire shaded region. in numerical order, preferably. So we have A union B is equal to the set that contains 1, 2, 3, 4, 6, 8, 10, and 12. As a matter of fact, we are going to be careful to leave out these elements because they are not in the union of the sets A and B. So next we are going to find the set A intersection B. A intersection B is a set that contains the elements that are common to both sets and is represented by the very dark region of the universal set, or the very dark region of the Venn diagram, which is this. This is a very dark region, and that represents the intersection of A and B. It is the region of the Venn diagram where A and B overlap. And those elements are 2, 4, 6, and 12. Do not forget that the union and intersection of sets are also sets and are therefore required to be suitably represented. Remember also that numerical order is appropriate. Find the set A union B all complement. A union B all complement is a set that contains all of the elements that are outside of the union of A and B. Notice that the complement sign does not apply to B only, but the entire expression that is inside of the bracket. So we have A union B and the entire thing enclosed in brackets complement. So we need the complement of the union of A and B. That is, all of the elements that are not in the union of A and B. And these are the elements. We have them right there. Write down all of the elements outside of the entire shaded region, and that will be our A union B all complement. And there we have them. Find the set A intersection B all complement. A intersection B all complement is a set that contains the elements that are outside of the intersection of A and B. That is, outside of the very dark region. So this is a region that represents the intersection. We want the complement of the intersection. That is, all of the elements that are not in this region. So we have 1, 3, 5, 7, 9, 11, and we have 8 and 10, preferably written in numerical order. So there we have A intersection B all complement 1, 3, 5, 7, 8, 9, 10, 11. As usual, sets are enclosed in braces and the elements are separated by commas. Numerical order is most appropriate where applicable. Find the set A complement union B complement. A complement union B complement is a set that contains all of the elements that are in A complement and B complement taken together. So we are going to take all the elements that are in A complement and we are going to take all of the elements that are in B complement and we are going to put them together. First, take a look at all of the elements that are outside of A. That is, outside of A, we have A complement. If we can remember, 5, 7, 9, 11, and we also have 8 and 10. So we have, in a short while, we are going to be required to remember this. This is the region that we are talking about for A complement. Take note of it. And of course, take note of those elements that are outside of B. These are the elements. Take note also and try to remember them. Write down all of the elements that were shown. That is, we are going to write down the union of A complement and B complement. Remember that A complement was everything outside of A, all of these elements. And B complement, everything outside of B, these elements. So we're going to write down the union of that set, which is all of these elements and all of these elements. So A complement union B complement is equal to the set that contains 1, 3, 5, 7, 8, 9, 10, 11. If the answer cannot be determined that easily, that is by visual effects, because we can just take a look. Some students will be able to do that, to take a look at the diagram and be able to do the analysis that we have just shown in order to write down the elements that are in A complement union B complement. But if the answer cannot be determined that easily, we can take another approach, which is write down the sets A complement and B complement. There we have A complement, there we have B complement. What do we want? We want the union of these two sets, A complement to be united with B complement. So we need the union of A complement and B complement, the set that contains all of the elements of A complement and all of the elements of B complement taken together, of course without repeating common elements. And there's our answer. We are going to take them from here. A complement union B complement is equal to 1, 3, 5, 7, 8, 9, 10, 11. That is all of the elements that we have right here without repeating common elements. Find the set A complement intersection B complement. Find the set A complement intersection B complement. A complement intersection B complement is a set that contains only the elements common to A complement and B complement. Right? So first, take a look at all of the elements that are outside of A. So we're going to look at A complement. This is A complement. It will do us well to remember this again. This region represents A complement. And we are going to do the same. Take a good look at all of the elements that are outside of B. These are the elements right here. Notice, these are the elements for B complement. For A complement, we had these. For B complement, we have these. We are going to take a look at the intersection, and we are going to write down the elements that are common. First, we have this. Then we have this. So the common elements are 5, 7, 9, and 11. Right there. That is the set A complement intersection B complement. And of course, if we cannot do it visually, we may write down sets A complement and B complement. So we write down the sets A complement and B complement. And then we need only the elements that are in both A complement and B complement. So we're going to search A complement and B complement to find the common elements. Let's see. We have a 5 there, yes. 7, 9, 11. So those are the common elements. 5, 7, 9, and 11. Remember, this and this. What do we have in common? This region. Notice that in this and the previous example, the same answer was obtained irrespective of the approach that was taken. Because of the laws of regular algebra, one may expect the following result. Right? So we are using the distributive law of regular algebra, and we are saying that A intersect B all complement is equal to A complement intersect B complement. We are also saying A union B all complement is equal to A complement union B complement. The operators, which are complement, union, and intersection, do not operate on sets according to the laws of regular algebra. The above results are therefore incorrect. Why are they incorrect? Because the operators that we have, complement, union, and intersection, as applied in set theory, they do not operate according to the regular laws that are used in algebra. We may be able to determine the correct result if we consider the results of the exercise that we have just completed. So then, if we take a look at the results of the exercises that we have just completed, then we will know the truth of it. If we take a look, we'll realize that what? those two are the same. Therefore, we are saying that A union B all complement is equal to A complement intersection B complement. And of course, the other two are equal. Notice that this set is equal to this set. Right. So, we have A intersection B all complement is equal to A complement union B complement. The result is called De Morgan's law and is very useful when simplifying expressions involving sets. The law is also applicable to the operations and, or, and complement resulting from gates in digital electronics. Any set of operations that adheres to the set of rules that include De Morgan's law is called a Boolean algebra. The principles were developed by the famous mathematician George Boole. Find the set A complement union B all complement. To find the set, we need to unite the complement of A with B. See? A complement union B all complement. So first we need to find what? The complement of A, and we need to unite that with B. So we find A complement and unite it with B. Then we are going to find the complement of the result. So to find the set, we need to unite the complement of A with B, then consider all of the elements that are not in the resulting set. If we need to find all the elements that are not in the resulting set, it means that we need to find the complement of the resulting set, which is what this is saying. That after finding the union of A complement with B, we then need to find all the elements that are not in that set, which is the complement of that set. So, first take a look at all of the elements that are outside of A. Of course, that will be A complement. So, A complement, these are the elements of A complement. And then what do we need to do? Take a look at all of the elements that are in B. Those are the elements that are in B. If you can remember, B is going to be united with A complement. Remember that A complement used to be these elements right here. So we have these elements representing A complement, and then we are going to unite that with B. So B is united with A complement. The only element that we are not talking about will be what? 1 and 3. So the union of B with A complement is all of these elements that we have right here. Therefore, those that are not involved, which would be the complement of the resulting set, will be the elements 1 and 3. So we do not need the elements that are involved. That is the one that we took a look at just now. We need the complement, that is, the set of elements that are not involved. The only ones that are not involved are 1 and 3. And there we have it, as we said before. However, we are going to take another approach in solving the problem. So this time we are going to take a what? A step-by-step approach. So first, write down the set A complement, which is this one. So A complement is that set that we had before. That's A complement. And then we are going to write down what? This set B, which is this one. B goes there. What do we want next? A complement union B. So let us do that then. Next, write down the union of A complement and B. That is, all of the elements of the two sets without repeating common elements. So we have A complement and B. So let us unite them. When we unite them, we get the set that contains 2, 4, 5, 6, 7, 8, 9, 10, 11, and 12. But this is not the set that we want. What set do we want? We want the set that is equal to the complement of this one. So we need the complement of this set, which is A complement union B, all complement. So we want the complement of this set, which is the elements that are not in this set. And if we go through all of these elements, we'll realize that the only two elements that are not present are 1 and 3. So the problem requires the complement of A complement union B. All of the elements that are not in the set, the only elements in the Venn diagram that are not in the set are 1 and 3, and A complement union B all complement is equal to 1, 3. The same problem, let us take yet another approach. This time we are going to use De Morgan's law. So according to the law, the complement of the entire expression will result in the complement of the individual sets. So remember De Morgan's law, if we are going to have A complement union B all complement, what are we going to do? This complement is going to be distributed inside here, but not according to the laws of regular algebra. First, we are going to complement the A complement. The complement of A complement is A. Next, we are also going to do the complement of union, which is the opposite of union, and then we are going to do the complement of B. So the complement of A complement is A. The reverse of this union is intersection, and the complement of B is B complement, and that is what we have right there. So the complement of A complement is A, the complement of union is intersection, the complement of B is B complement. Therefore, we are required to find A intersection B complement. So write down the elements of A, and then write down the elements of B complement. There we have them. What do we need? We need the intersection of A and B complement. So in here, we need the intersection of the two sets. That is, the elements that the two sets have in common. What are the common elements? If we go through here, we realize that 1 is present in both, 3 is present in both, and then we may not be able to find any other element. So we have A intersection B complement is equal to 1, 3. And of course, that is equal to the result that we got on the two previous occasions. We need also to find the set A intersection B complement all complement, and we are going to take all of the three approaches that we did with the other problem. So to find the set, we need the complement of the common elements of A and B. First, take a look at all of the elements that are in A. Then take a look at all of the elements that are in B complement. So, we just took a look at the elements that are in A and the elements that are in B complement, this. So this is A and this is B complement, and we want the elements that are in common. So what elements are in common with this and then this? A and B complement. Obviously, the elements 3 are the ones that we have in common. However, we do not want A intersection B complement. We want the complement of that. That is, all of the elements that are not in A intersection B complement. So, this is A intersecting with B complement. We get 1, 3. Therefore, the set that we want is the set that contains all of these elements. So, all of the elements with the exception of 1 and 3. So, if we can identify the common elements, the required set will contain all of the elements of the Venn diagram with the exception of those. Of course, the common elements of A and B complement are 1 and 3. But we want the complement of that. Therefore, we want all the elements that are in the Venn diagram with the exception of 1 and 3, and this is what we have. So we have just used the Venn diagram, taken a graphical approach to solving the problem, but we have other approaches that we'll take in a short while. The same problem that we have right there, and we are going to take a step-by-step approach this time. So first we write down the set A right there, then we write down the set B complement right there. Now we need what? The intersection of A and B complement, that is the set of elements that are in A and they are also present in B complement. There's A, there's B complement, and we are not going to repeat common elements. So next, write down the sets of elements that are common to the two sets. Oh, the only two elements are 1, 3. So we need not A intersection B complement, as we see here. We need A intersection B complement, all complement. That is, we need all the elements of the Venn diagram that are not in this set. So we now need the complement of the set. This involves the elements that are in the Venn diagram with the exception of 1 and 3. There we have them. All of them with the exception of 1 and 3. And of course, that is equal to 1 that we had before. So find the set A intersection B complement, all complement, which is the one that we have just found. But we are going to use De Morgan's law. According to the law, the complement of the entire expression will result in the complement of the individual sets and a change in intersection to union, and so on. So we are going to say, since we have this all complement, we are going to take the complement of A, which is A complement. We are going to change intersection to union, and we are going to take the complement of B complement, which is B. So write down the elements of A complement. Write down the elements of B. Of course, we need the union of A complement and B. So all of the elements that are in these two sets without repeating common elements. So we need the union of the two sets, all of the elements of the two sets. Let us write them down, and that is our answer. Whenever the number of elements to be included in a Venn diagram is very large, or the nature of the study dictates, the number of elements in the Venn diagram is used rather than the elements themselves. To simplify the manipulation of the numbers of elements in a Venn diagram, mathematical formulae may be derived. A simple question may be used as the basis on which a formula may be derived. And we're going to do that on this occasion. The question is, given that NA is 34, the number of elements in A is 34, and NB is equal to 40, find NA intersection B if NA union B is equal to 50. So right away, we can just take a quick look at it. NA is 34, NB is 40. Put them together, it is going to be more than 50, which is 50 is the number of elements in the union of the two sets. So we have probably a paradox right there, so we are going to take a look at how we are going to resolve that. By basic common sense, if NA is 34 and NB is 40, and combining the sets NA union B is equal to 50, which is less than the sum of the number of elements in the individual sets, then the number of elements that are repeated, that is, those are in the intersection, must account for the difference. So, 34 plus 40 is 74, but n A union B is 50. So n A intersection B must therefore be the difference. So 74 minus 50 is equal to 24. So we have 24 elements in the intersection of the two sets. So let us take a look at how the calculation may be used to derive the formula. So we have 34. Can you remember what 34 represented? What 40 represented? What 50 represented? And what 24 represented? If not, we have it right there. Right here we have 34 is NA, 40 is NB, 50 is the number of elements in the union of the two sets, and 24 the number of elements in the intersection of the two sets. It is more appropriate to make the number of elements in the union of the two sets the subject of the formula. A simple transposition will yield the following. So, the number of elements in the union of the two sets will more appropriately suit the subject of the formula. So we are just going to use a simple transposition in order to make it the subject. And when we transpose, that is what we have. Number of elements in A union B is equal to number of elements in A plus number of elements in B minus number of elements in A intersection B. We may use a method of induction to derive the formula for the number of elements in three sets. We need to be aware of the fact that there will be three intersections of two sets. So we are going to have A intersection B, A intersection C, and B intersection C. So we will have, instead of one intersection of two sets, we will have three. In addition to that, there will be an intersection of three sets. Notice that on the left hand side we have the number of elements in the union of the two sets. The same will be true for the union of three sets. So we have on the left hand side the number of elements in the union of the three sets. So we are drawing an analogy between the formula for the number of elements in two sets and the number of elements in three sets. We have the sum of the number of elements in the individual sets. So the number of elements in the individual sets are added right there. We will do the same, but we will have three sets this time instead of two. So we have them right there. What about the intersection? Notice that the number of elements in the intersection of the two sets is subtracted. We will therefore subtract the number of elements in each of the intersection of two sets. Do not forget that there are three of them. So when we have the sets taken two together, we are going to subtract all of the number of elements in those intersections. So we have subtracting NA intersection B minus NA intersection C and minus NB intersection C, because we are saying that if we have intersection of two sets, they are going to be subtracted in the formula. What about the intersection of three sets? Because this formula is for three sets. Now, the induction becomes very important. We have the number of elements in the intersection of three sets. What do we do with it? Look what we have. The numbers of elements in the individual sets are added. So we have add. Then the number of elements in the intersection of two sets are subtracted. First, we add, then we subtract. The number of elements in the intersection of three sets must be added if we are adhering to the pattern alternating addition and subtraction. So if we start with addition, then we move to subtraction, then we have to move to addition again, in order that we might have completed the pattern in alternating the addition and subtraction. The formula seems long and cumbersome, but it is really very simple. As in most topics in mathematics, an understanding of any device will simplify its use. So if we can identify it, then we can use it quite easily, making life very simple for us. All it means is that the number of elements in the union of three sets may be determined as follows. Add the number of elements in the individual sets, subtract the number of elements in the intersection of two sets, add the number of elements in the intersection of three sets. In a short while, we will do some exercises and verify the simplicity with which the formula may be applied. We are in the problem solving section, and we are going to apply the formulae and other skills that we have learned in set theory. This first problem says, out of 136 students in a school, 60 take French, 100 take chemistry, and 48 take physics. If 28 take French and chemistry, 44 take chemistry and physics, and 20 take French and physics, how many take all three subjects? Now this is more than a mouthful, so what we are going to do is rewrite the problem in a short and symbolic form. So we have 136 students in the school, 60 take French, 100 take chemistry, 48 take physics, 28 take French and chemistry, 48 take chemistry and physics, 20 take French and physics, and we do not know the number of students who take all three subjects. Let us represent it by the unknown x. So x is going to represent the number of students who take all three subjects. The subject of the formula is the number of elements in the union of the three sets. So 136 students in the school, and that number will represent the number of students in the union of the three sets, and that is usually on the left hand side of the equation. Then first, on the right hand side, we have the sum of the number of elements in the individual sets. Remember that? The number of elements in the individual sets, we add them on the left hand side. So we have 60, 148, and we have them added right there. Then we subtract the number of elements in the intersections of the two sets. So we have those who take French and chemistry, chemistry and physics, physics and French. We subtract those on the right hand side as dictated by the formula, and then of course the number of elements in the intersection of the three sets, which is the unknown, is also added. So remember the pattern that we have developed? Taking them one at a time, we add. Taking them two at a time, we subtract. Taking them three at a time, we add again. So we are going to simplify with some arithmetic. So we are going to add those, and of course in directed numbers, what do we do? If we are adding numbers that have the same sign, we add all the values and the answer will have the same sign as those numbers that we have added. So when we add them, we get 92, so the result is negative 92, and of course the unknown is not to be left out and occupies its position right there. And of course we have a simple linear equation, and we are going to transpose that equation in order to solve for x. So of course the 92 that we have subtracted here is transposed to a positive 92 on the other side, and this 208 that has no sign in front of it, we are sure that it is a positive 208, so by transposition on the left hand side, it becomes a negative 208. 228 minus 208 is equal to 20. X is equal to 20. In the application, it is not necessary to write the long and cumbersome formula. If students are aware of the significance of the symbols and their arrangement, they will have no problem with it. The sum of the number of elements in the individual sets go first. Next, we subtract the number of elements in the intersection of two sets. And we finish up by adding the number of elements in the intersection of all three sets. If we have another problem, in an examination, 60 candidates offered mathematics, 80 offered English, and 50 offered physics. If 20 offered mathematics and English, 15 English and physics, 25 mathematics and physics, and 10 offered all three, how many candidates sat the examinations? So we are going to write the problem in a short and symbolic form. So 60 candidates offered mathematics, 80 offered English, 50 offered physics. Then we have the intersection of two sets, 20 English and mathematics, 15 English and physics, and finally 25 mathematics and physics. And of course, the intersection of three sets, not to be left out. So, the number of elements in the union of the three sets is unknown. So let us represent it by X. So X candidates sat the examinations. We do not know the number of elements in the union of all three sets. So that occupies the left-hand side. The number of elements in the union of the three sets occupies the left-hand side. Then we have on the right-hand side, we are adding the number of elements in the individual sets. That's what we usually do. And then what do? We subtract the numbers of elements in the intersections of two sets. And finally, we add. Don't forget our pattern, add, subtract, add. And if we simplify, this is the result that we will get. So X is equal to 40. This is how simple the application of a formula can prove to be when we understand the principle on which it is based. This is true irrespective of the topics or the subject to which it pertains. Here we have yet another problem. Of 100 students, 42 take physics, 35 take chemistry, and 30 take botany. 20 take none of these subjects. 9 take botany and physics, 10 take botany and chemistry, and 11 take physics and chemistry. Our duty is to find the number of students that take all three subjects, and then the number of students that take physics only. Then we move on to the number that take botany and chemistry only. Now, there's no use we go trying to decode this problem because we are fully aware of the contents and intricacies of this problem. We know that we have to take the number of elements singly, we have to take them two at a time, and we have to take the intersection of three sets. Right? So, there's no need beating around the bush when we are sure that is all the problem will entail. So, we write the problem in a short and symbolic form, and that is how short it can be, the entire problem, no problem whatsoever. The number of elements in the intersection of the three sets is unknown. So let us represent it by X. So the number of elements in the intersection of three sets unknown. 20 take none of the subjects. This is not a typical entry in the set equation, so let us include it at the end. Right? So the 20 that take none of the subjects is included at the end. It is not typical. in set theory. But of course we can use common sense and we will apply it to the set equation also. So 100 students, we have them right there. And of course we are going to take them one at a time and add them. 2 at a time we subtract. 3 at a time we add. And then now we are going to focus on the 20 that take none of the subjects and are therefore not a part of the union. So 20 should be taken away from the total number of students, because 20 students take none of the subjects. That 20 will not be a part of the union. So we have 100 right here on the left hand side, and 20 of them do not belong to the union. So we subtract 20. So the simplification gives 100 minus 20 is 80, and if we put all of these together we'll get 77. So 3 is equal to x and x is equal to 3. We have solved part A. The number that takes all 3 subjects is 3. We will now use a Venn diagram to assist in solving parts B and C. So let us draw a Venn diagram in which the sets are labeled with the letters that start the name of the subjects. So there is our Venn diagram. We have the universal set Xi, and we have P for physics, B for botany, and C for chemistry. And 20 take none of the subjects, so the 20 that take none of the subjects goes in the universal set only. So none of the subjects, it's not in P, not in B, not in C, but it is inside of the Venn diagram. 3 take all 3 subjects. So when placing numbers in the sets of a Venn diagram, place a number in the intersection of the 3 sets first. So that is where we place it, the intersection of the 3 sets first. 3 take all 3 subjects. Then information will be placed in the intersections of 2 sets. B and P have 9 elements. That is, botany and physics have 9 elements. But 3 of them are already accounted for. So let us look in the Venn diagram. We see what? Botany and physics. And they overlap right here. And we have 3 elements there already. So with a total of 9, the number that should go here is 9 minus 3, which is equal to 6. Goes right there. Botany and chemistry. Right here. We have what? 10 take botany and chemistry. But we have 3 accounted for already. So the number that will go in this region that represents botany and chemistry only will be 10 minus 3 equals 7. Botany and physics. 11 minus 3, because 11 take physics and chemistry. So then we will have 3 being accounted for already. So the rest of that is 8. 42 take physics. So let us go to the region that is represented by those who take physics only, which is this region. So 42 in physics, but notice that this set that we have here, 6, 3, and 8 elements are there already. So those elements are accounted for. So what do? We subtract all of them from the 42 and we get 25 elements. Chemistry only. 35 minus 3 minus 8 minus 7. Why? Because in chemistry, as it is stated here, we have all of 35. But this is our set, chemistry, that has 8, 3, and 7 already. So the rest of chemistry is 17, and it goes right there. And we are going to do the same thing with botany. And, of course, since we have 30, we are going to take away the 6, the 3, and the 7 that we have already represented here. And the result is 14, and it goes in botany only. The answer to part B, the number who take physics only, how many take physics only in this region? 25. The answer to part C, the number that take botany and chemistry only, is 7. So we have botany and chemistry. But the region for botany and chemistry is all of this. Botany and chemistry. However, we have 3 right there in physics also. So then, those that are in botany and chemistry only will be those in this region right here. And of course, we have 7 elements. Some students always ask, what is botany? Well, biology is divided into 2 studies. The study of plants and the study of animals. And that's not where the word bi comes from. The word bi comes from the Greek word bios. That means life. And ology comes from the word logos. So we have bios and logos. And logos means the study of, and bios means life. So biology is the study of life and has nothing to do with the fact that it is divided into 2 sections, botany and zoology. So botany is the study of plants and zoology is the study of animals. And in the olden days, that is before I entered high school, those subjects, botany and zoology, used to be taught separately. And of course, if you go to the university, you can do both of them separately. Consider the following 3 statements. Some students play basketball. Tall students are over 2 meters in height. All basketball players are tall students. Represent the statements in a suitable Venn diagram showing and stating an appropriate universal set. Show on your Venn diagram, Nina is 1.5 meters tall, and also Robert, who is 2.2 meters tall, does not play basketball. The 3 statements that are used to give information are all about students. The universal set is obviously the set of all students. Even if the 3 statements did not have students, the universal set has to be the one that will be able to contain all of the other groups that are spoken about. We may begin our Venn diagram with the universal set being the set of all students, or just the set of students S. So we're going to call that set of students S, and that is for the universal set. Tall students are over 2 meters in height. Statement number 2 is not about sets. It just gives us information about the students who are considered to be tall. So it's not about this set and may not be used to determine the relationship among the sets. So the other 2 statements will give us information about the relationships of the sets to each other. So all basketball players are tall students. The final statement is enough to tell us the relationship between the sets. It means that the set of basketball players B must be contained in the set of all tall students T, because it says that all basketball players are tall. So the set of basketball players must be contained in the set of tall students. as we have it right there. Some students play basketball. Although the first statement was not essential in constructing the Venn diagram and may be trivial because all other sets must be contained in the universal set, it helps to remove any ambiguity about the identity of the universal set. So we have Nina is 1.5 meters tall. Where will Nina go? Nina does not meet the requirement to be considered tall. Remember that tall students are over 2 meters in height. She is therefore placed outside of the set of tall students. So this is our set of tall students. So Nina must be placed outside of that set. Robert, who is 2.2 meters tall, does not play basketball. So Robert meets the requirement to be considered tall. However, he does not play basketball. He is placed inside of the set of tall students, but not inside the set of basketball players. So there is where Robert has to be, inside of the set of tall students, but does not play basketball, not inside of the set of basketball players. You were warned in the introductory statement that you will be required to solve problems that required much more imagination than understanding the principles of set theory. And of course, that problem is a proof of that fact. Practicing problems and set theory will help to develop the skills required to answer examination questions. This is necessary but not sufficient, as examiners always take the opportunity to create situations that require students to think, and most times situations that are unfamiliar. There are 100 members in a foreign language club. 48 members speak Spanish, 45 members speak French, 52 members speak German, 15 members speak Spanish and French, 18 members speak Spanish and German, 21 members speak German and French. And in all of this, remember that there are a few things that we are paying attention to. Number of elements in the individual sets, number of elements in the sets taken 2 at a time, and number of elements in the set taken 3 at a time. Now each member speaks at least one of the 3 languages. So write an algebraic expression to represent the number of members in the shaded region. Of course, we do not have a shaded region because we do not have a diagram. The diagram is going to be presented in a short while. So write an equation to show the total number of members in the club. Hence, determine the number of members who speak all 3 languages. In order that we might have enough space on the slide, let us rewrite the problem in symbolic form. The set of those who speak Spanish is S, those who speak French is F, and those who speak German is G. Of course, there we have our problem in symbolic form, short and less cumbersome than we had it before. Now, we are going to take a look at the part of the problem that says, write an algebraic expression to represent the number of members in the shaded region. And of course, describe the shaded region. So, that's what we are going to do first. The shaded region is a part of the intersection of the set Spanish and German. Specifically, the portion that does not intersect with the set French. So we realize that it is a part of the Spanish and German, but it does not intersect with French. So the algebraic expression that we need to write is what? This portion, 18 speaks Spanish and German. So the total in this region is equal to 18. But X is not a part of it. So there we'll have what? 18 minus x. So the total number who speak Spanish and German is 18, and the number who speak all three languages is x. The number in the shaded region is 18 minus x. The shaded region represents those who speak Spanish and German but do not speak French. Write an equation representing the total number of members. Of course, there are 100 in the club, and that 100 will represent the union of the three sets. Then we take the number of elements in the sets individually, and of course they are added on the right hand side. And of course, if you are going to take the two at a times, we subtract them on the right hand side. And of course, add the number of elements in the intersection of the three sets. It is the unknown x, so that is added right there. And then when we simplify and solve for x, that is our result. So x is equal to 9. So we have another problem that says 68 students in Form V. 15 study mathematics only, 12 study physics only, 8 study physics and chemistry only, 2 study physics and mathematics only, 3 study mathematics, physics and chemistry, 4 study none of these subjects, and we are required to draw a Venn diagram that is labeled to represent the information. Then we determine the number of students who study physics, and look at this problem, a little bit of a mouthful. Given that X students study mathematics and physics only, and twice as many study chemistry only, write an algebraic equation to represent the information given, and hence calculate the value of X. So the presence of the word only in reference to a section of the Venn diagram simplifies our work in two ways, because we have only here, study mathematics only, 12 study physics only, and so on. We have two ways in which that simplifies the work with the Venn diagram. One, we do not need any special calculation. And two, we need not be mindful of the order in which information is entered. So we just say mathematics only, 15. Physics only, 12. Physics and chemistry only, 8. And then 2 study physics and mathematics only. That goes there. 3 study mathematics, physics and chemistry. That is 3 study all 3 subjects. Usually we will enter the information in the intersection of the 3 sets first, which is this bit of information would have gone in the Venn diagram before any other. But because of the onlys that we have here, then we do not have to exercise any strict adherence to that rule. So 4 study none of these subjects, and the 4 that study none of these subjects will go right there. Determine the number of students who study physics. Given that X students study mathematics and chemistry only, and twice as many study chemistry only, write an algebraic equation to represent the information given, and hence calculate the value of X. Now we will determine the number of students who study physics, and of course it says given that X students study mathematics and chemistry only, and twice as many study chemistry only, write an algebraic equation to represent the information given, and hence calculate the value of X. So determine the number of students who study physics. of course, there we have it. In physics, we have 12, 2, 3, and 8 students. So, adding all of those together, we get 25. And this one is saying now, given that X students study mathematics and chemistry only, and twice as many study chemistry only, write an algebraic equation to represent the information given, and hence calculate the value of X. So X study mathematics and chemistry only, as we have them right there. Mathematics and chemistry only is X. And the other statement says, twice as many study chemistry only. There we have it. So we are going to write the algebraic expression. And what do we have? The total number in the school, as we had in the beginning, the original statement of the problem, we have 68. So in that 68, we are going to use a strategy. Instead of writing down a lot of numbers, we know that physics alone has 25 students, so the 25 students of physics will go next. And of course, the rest will be added on the right hand side. So we have that 15 plus x plus 2x. That will go next. So 15 plus 25 is 40, and x plus 2x is 3x. We have 4 students that are not in the union of the 3 sets, but they are also in the universal set. They are also included in the 68, and they take up their position on the right hand side of the equation also. So we have 25 plus 15 is 40, plus 4 is 44, and we have x plus 2x is 3x. And of course, if we transpose the 44 to the left hand side, we will have a negative 44. So 68 minus 44 is 24, and that is equal to 3x. So dividing, we have 8 is equal to x, so x is equal to 8. This is our good friend. We have the universal set is equal to the set of 3, 6, 9, 12 to 27. And that, of course, the set of multiples of 3 beginning at 3 and ending at 27. And if that is the universal set, E, that we have, the set of even numbers right here, is required to be inside of that universal set. So all the elements of E are required to be in this set, and of course all the elements of G, which is greater than 20, are required to be in this set. And of course, E and G are subsets of U. Well, in the case that we are speaking about universal set, there is no doubt that all the sets being spoken of are contained in the universal set. Our first requirement is to list the members of E and the members of G. The universal set is a set of those multiples of 3 from 3 to 27. So E being the set of even numbers, multiples of 3 from 3 to 27, the even numbers are 6, 12, 18, and 24. The set G is a set of multiples of 3 from 3 to 27, but the ones that are greater than 20. Of course, we have the ones that are greater than 20 are 21, 24, and 27. Draw a Venn diagram to represent the above data. So we are going to draw our Venn diagram. U is the universal set. The set of even numbers in that set is E. And the set of numbers that are greater than 20, that is represented by G. The element in the intersection of E and G is entered first. is there an element that is in E and is also in G? That one is entered first, and that is 24. Next, we have the unique elements of E. So, the elements that are not a part of the intersection but are contained in E, they will be next. Of course, we will follow that by the unique elements of G. So those elements of G that are not in E, they will go next. Finally, those elements unique to the universal set, that is, the elements that are in the universal set, but they are not in E and they are not in G. Right. So we are going to state the number of elements in E union G all complement. Now, on seeing this, some students will write down the elements in E union G all complement, but that is not what is required. We need the number of elements in E union G all complement. Take note that the problem requires the number of elements in the set and not the set itself. And E union G all complement, those elements that are not in the union of E and G. So the elements that are not in the union of E and G are 3, 9, and 15. But the question did not require that we have or we write down the elements. The problem required that we state the number of them. So how many? 1, 2, 3. So N E union G all complement is equal to 3. Finally, there are 50 students in Form 6. All students study mathematics. 17 study biology. 18 study chemistry. 24 study physics. 5 study physics, chemistry, and mathematics. 7 study physics, biology, and mathematics. 6 study chemistry, biology, and mathematics. 2 study all 4 subjects. And we are required to draw a carefully labeled Venn diagram to represent the data, using the universal set as the set of students who study mathematics. Determine the number of students who study at least 2 subjects. Calculate the number of students who study mathematics only. The key to solving this problem is to be aware that the universal set is a set of students who study mathematics. Of course, it was not hidden. It says so right here. Using the universal set as a set of students who study mathematics. Because the universal set is a set of students who study mathematics, we may place a little emphasis on mathematics while entering the information in the Venn diagram. So here is our problem in short. And to study all 4 subjects. But do not forget that while we have the intersection of 3 sets right here, the intersection of 3 sets is also in the set of students who study mathematics. Therefore, that accounts for the 4th set. So, information will go in the intersection of the 3 sets first. Why? Because although we have 3 sets intersecting here, mathematics is also a subject and all other set is contained inside of the set of the students who study mathematics. So that accounts for the 4th set. So we are going to be looking at the intersection of 2 sets, bearing in mind that mathematics is the universal set. Next will be the intersections of 2 sets. Do not forget that each intersection of 2 sets already contain 2 elements. So, of course, if we are going to be looking at physics and chemistry, because mathematics is a universal set, we are looking at physics and chemistry. Physics and chemistry. We have 5 students in physics and chemistry already. We have 2 elements in physics and chemistry already. So, we need 5 students to be inside of the intersection of physics and chemistry. But 2 are already accounted for, so difference will go right here, which is 3. And physics and biology, 7 minus 2, because we have 7 studying physics and bio, and 2 are already accounted for, so we have 5 right there, and for 6, 2 are already accounted for, so we have 6 minus 2 is equal to 4. Then we are going to go to the number of elements that are in the individual sets. First we will consider the individual sets, but not without the members that are already present in them. So we are going to be looking at what? 17 study biology, but of course we have elements in biology already. So we have to consider these. These are a part of the 17, so what number will go right there? 17 minus the 5 that we have here, minus the 2 and minus the 4, and the remainder will go right there, which is 6. And we do the same for chemistry. 18 in chemistry. Here we have chemistry that has 4, 2 and 3. So it is 18 minus 4 minus 2 minus 3, and that is 9. And of course, same treatment for physics with 24. Physics we will subtract 5, 2 and 3, and we get 14. Those who study at least 2 subjects, mathematics and at least 1 other, will be all of those in the union of the 3 sets. Let us do a little analysis. How many subjects do these students study? These are in the set of what? Chemistry, biology, and physics. So that's 3 subjects. However, it is in the universal set, which is the set of students who study mathematics. So that means these 2 individuals that we have right here study 4 subjects. These study bio and chemistry. But these 4 are also in the universal set. So these 4 study bio, chemistry, and mathematics. 3 subjects. This number that we have here represents 6 students who study biology, but not biology only, because these students also study mathematics. So they study 2 subjects. So those who study at least 1 subject, that means, what do we mean by at least? 2 or more. So we are saying that those who study at least 2 subjects must be those who study 2 or more subjects. And those who study 2 or more subjects are those who are in the union of the 3 sets, and we need to add those up. But instead of adding all of these individual numbers to make a long string of numbers, we are going to choose the largest number here, which is 24. So in physics we have 24. So we'll just put 24 down, then we add the 6, the 4, and the 9. So in all of this we have 24 goes there, and then we are just going to add the 64 and the 9 instead of adding all the numbers. And then we have 43. So 43 study at least 2 subjects. Those who study mathematics only are the rest of the 50. So mathematics only, those who are in the Venn diagram but not in the union of the 3 sets, those will be the rest of the 50. 50 minus 43, and that is equal to 7. Members of the public have been exposed to Richard James mathematics resources before all of the volumes were finished, and there was a great demand for set theory. Strangely enough, it ended up in the last volume, not in number, but in the sequence that they were completed. It is my hope that no one will consider Richard James' resources to be lacking in any good thing. And of course, that is in hope more than any real conviction. Remember the problem with the multiples of 3. It was mentioned in the introduction. Now that we have seen its solution, you may be thinking that anyone who got it wrong would be crazy. Well, wait until you make a meal of some simple problem that did not have any example in Richard James' mathematics resources. Another set of horrible answers came from the problem with the 4 subjects. Some students tried to place the set 4 subjects inside of a universal set, neglecting the fact that the universal set is a set of students that study mathematics. I cannot remember in all my life a single situation in which a problem had 4 intersecting sets inside of a universal set. I truly hope this time that the presentation met the expectations that you may have had from observing the introduction. If nothing else, that set theory requires thinking.